Hi everyone. So till now we have seen MOS physics, we have seen the internal structure, we have seen the current equations, we have seen saturation region, triode region and the current equation. We have also seen how to find the region of operation. So these kind of question we have seen. In the previous assignment, what did we show? We had some particular configuration given and there were some DC bias there. It could be voltage, it could be current. So there was some DC bias and based on that we were finding the region of operation. So what do you mean by bias? Bias means simply applying some DC. It can be voltage or it can be current. So this is what we have written. The process of setting DC operating voltage or current condition to the correct level so that an AC input signal can be amplified correctly by the transistor. So what do you mean by AC input signal that can be amplified? That we will see. But the meaning of biasing is just giving a particular DC supply. It could be a voltage, it could be a current. So let's assume this is my transistor. So I am giving a particular voltage supply to it. Some VDD I am giving, and then this VDD can drive some current that I can call ID. I am giving some voltage supply. In the previous question we could see 5 volt, 10 volt, 100 microampere current. So the some supply we are giving, that's it. Now why is it necessary to give the supply? Why cannot I run the transistor without even giving the supply? So why I needed the MOSFET? In the first lecture when I started MOSFET, I told you why I needed the MOSFET. Why I needed MOSFET? To amplify my signal. Let's assume I am applying some voltage here, 20 millivolts sin omega t. I needed to amplify it. So let's assume in output I am getting some 100 millivolts sin omega t. So this is why I needed it, so that it can amplify my input signal. One more thing I would like to tell you, here we will always amplify small signal only. We can't amplify large signal. What do I mean by small signal? Small signal means the amplitude is small. I cannot amplify large signal. Let's talk about this this mic. The same example I gave you when we were studying diode circuit. So let's talk about this mic. This mic has two things. One is the DC bias, which it is getting from this laptop. Some DC voltage it is getting. That is helping for this microphone to turn on. उस DC bias से microphone turn हो जाएगा. Then there is this voice input. I am giving some voice input here, and then this voice input is being amplified. So this particular microphone is getting two inputs. One is the bias, one is the DC bias, and the other one is my voice. That is a small signal. The bias it might be getting 2 volt, 0.8 volt, 0.5 volt. Then there is my signal. So all these signals which needs to be amplified are small signal only. It has amplitude 20 millivolt or 40 millivolt. So all those signals are small signal. It cannot happen that I can apply 2 sin omega t and then I will amplify it. No. This much of large signal cannot be there. So that's why they ask you in the question that find the small signal voltage gain. That means small signal input is applied. Some people confuse it with frequency. It has nothing to do with the frequency. The only meaning is the amplitude is small. So this is why I needed my transistor. Let's assume I apply 20 millivolt and then I get 100 millivolt sin omega t. So that was the reason why I needed my transistor. Now what if I don't even apply the DC bias? I only apply the small signal. So what was my small signal? What if I apply only small signal? There is no DC bias. I am telling you the reason why I need DC bias. So what if I don't apply any DC bias, only I apply small signal? What will happen? In this case, what is the value of VGS? Here, in this case, what is the value of VGS? VGS turns out to be 20 millivolt sin omega t. So maximum value of VGS is 20 millivolt and minimum value of VGS is minus 20 millivolt. Let's plot ID versus VGS. VT will be some 0.5 or 0.7 or 1 volt. Let's assume my VT is 1 volt. VT cannot be so small, 0.02. 20 millivolt cannot be VT. VT will be 1 volt, 0.5 volt, 0.7 volt. At least this much value will be there. Where will be this 20 millivolt? It will be somewhere here, right? Or more nearer, but somewhere here. This 20 millivolt will be in this range. Tell me, will the transistor turn on? Your VGS value is so small that transistor is not even turning on. That's why you need to give the DC bias. Are you getting this point? Transistor लैग कर रहा है यार थोड़ा सा. ट्रांजिस्टर doesn't even turn. Oh. Okay, let me refresh it once, then I will start the video. Yeah, so I was saying that transistor doesn't even turn on. So to turn on the transistor, we have to give that DC bias, and then on that we can superimpose or we can apply the small signal. Are you getting this point? We did the same thing in the diode circuit as well. What did we do in the diode circuit? In the diode circuit, first we turned on the diode. We had two signal here. One was DC and then the other one was, this was the DC and then we had applied some AC. So what this DC signal was doing, it was turning on the diode, and then what this AC signal was doing, if the diode is turned on, then based on the diode current, we were getting a small signal resistance, that was neta Vt upon I diode. So in the small signal AC analysis, we were replacing this diode with the small signal resistance. That's it. This is what we were doing when we were studying the diode circuit. It is again lagging. Okay. Yeah. So here also we are doing the same thing. We are applying a DC signal that will make sure that our transistor is turned on, or in whatever region we want it to operate. It can be linear region, it can be saturation region. That we will learn in the future, that my transistor is turned on. So in what region I would want it to operate, linear or saturation. So that we will learn in the further part of the video. So here my primary target is to turn on the diode, not the diode, the transistor. So my primary target is to turn on the transistor. So for that I will give a DC bias, this VGG, and then a small signal voltage. So VGS would be DC bias plus the small signal voltage, that is 20 millivolts sin omega t. Now since this is a small signal voltage, you will not have to worry whether it may turn off my transistor. What I mean to say, let's assume if it was large, let's assume the DC signal I gave is 2 volt, okay, and the signal, the AC signal that I am applying is 1.5 sin omega t, and value of Vt of my transistor is 1 volt. Then what will happen? The minimum value it can attain is minus 1.5. So 2 minus 1.5, at some value you will get your input voltage to be 0.5 volt. So your transistor may get turned off. But since this is a small signal voltage, 20 millivolt is a small signal voltage, the region of operation will not change, because there will be a very small change. There will be a very small change in VGS. What that change will be? Very small change. That will be, maximum voltage will be 2 plus 20 millivolt, that would be 2.002 or 002. 002 will be 2 millivolt only, so 02, and minimum would be 1.98. So that is very near to 2 only, 2.02 and 1.98, very near to 2 only. So your operating condition will not change. Your operating condition will be the same. If it is running in saturation, it will be in saturation only. If it is running in linear, it will be in linear only. So that's why the applied input, the applied AC signal that we want to amplify, that is small. So we can draw it like, how will my VGS look like? So my VGS will be simply a DC plus a small signal. This will be my VGS. Versus time we are drawing. So this is the DC, that is 2 volt. 2 volt I can show here. 2 volt plus 2 volt plus the AC signal. That is imposed on it. So this point will be 2 plus 20 millivolt, and this point will be 2 minus 20 millivolt. So it will not change the operating condition. Let's see it in one more graph. We will see it in the ID versus VGS graph. So this is our ID versus VGS transfer characteristic. I am assuming my VT voltage to be 1 volt. So where will be my operating condition? This is my operating condition. I am running it at 2 volt plus 20 sin omega t. 20 millivolts sin omega t. So this is my operating condition. So my operating condition will be somewhere here. Let's assume this is my operating condition. Let's assume this is 2 volt. So what this point will be? Although it will be very nearer, but to show you in the graph, I will make it far away. So this I am thinking this will be 2 plus 20 millivolt, and this will be 2 minus 20 millivolt. So I don't need to write it down. So this is 2, this point will be 2 plus 20 millivolt, and this point will be 2 minus 20 millivolt. So basically what is my signal? My signal is something like this. My signal is 2 plus 20 and 2 minus 20 and sinusoid. So my signal is something like this only. This is my signal. बन जा भाई सही से. VGS is the input. Input I am applying 2 plus 20 and 2 minus 20. That's why I showed it like this. It is my input only. And with respect to this input, what I am getting at the output. Let's assume if my input was 3 volt. So with respect to 3 volt, this was the ID I was getting. Right? If my input is 2 volt, with respect to this 2 volt, what ID I will get? With respect to this 2 volt, what ID I will get? This ID I will get. This ID I will get. If my input is 2 minus 20 millivolt, with respect to that input, what ID I will get? This ID I will get. And if my input is 2 plus 20 millivolt, what ID I will get? This ID I will get. Are you getting this point? So at 2 volt, this ID I am getting. At 2 plus 20, this is 2 plus 20, this ID I am getting. At 2 minus 20, this ID I am getting. So this kind of waveform I am getting. I can make a better waveform here. So when you apply this sinusoid input, with respect to that input, you are getting this output. Are you getting this point? So this was the case when my VGS is 2 plus sin omega 20 millivolts sin omega t. When my VGS is, I will apply two kind of VGS. First one I am applying 2 plus V in, small signal voltage. Now the second VGS I will apply is 4 plus V in. Now I am taking VGS value to be 4. So my DC bias is 4. So it could be somewhere here, could be somewhere here, and then plus minus 20, plus minus 20, minus 20 and plus 20. थोड़ा और आगे बनाना पड़ेगा. Gap should be similar, no? Gap is the similar now. This is 4 volt. Here this is 4 plus 20, here this is 4 minus 20. So this is my input. With respect to this input, what I am getting? What output I am getting? When you apply this input, this is the output you are getting. Output is very much amplified. You can see it, right? This was your input, output is very much amplified. Here this range is same, that is 40 millivolt. This is same, but here the amplification was this much. Here the amplification is this much. Here your magnitude has increased. So what did you see here? When the slope is higher, at this point this was the slope. The graph is going something like this, like this. The slope is continuously increasing. So the point where the slope is higher, you are getting more current in the output, and if there is more current, that means there will be more gain. Why so? Because this is your MOS. Let's assume this is your MOS, and this is the VGS, and then you have a ID, and this is your load RL. and let's assume you are collecting your output here. Based on your VGS, you are getting more current. If you are getting more current, that means there will be more voltage drop across RL. If the current is more, there will be more voltage drop across RL. That means the V0 value will be larger. If V0 value is larger, that means there will be more gain. That's it. If V0 value is larger, that means there will be more gain. If V0 value is low, the gain is low. So more ID, that means more gain. So when your slope is higher at the point, this point, when your slope is higher, your gain is more. So here I can write del ID by del VGS at what point? At VGS 2 is higher than del ID upon del VGS at point VGS 1. So I got to know that in this case I will get more gain. In this case I will get more gain. Here I am getting more gain. So now this parameter becomes an important parameter, that is output current divided by input voltage. Now this is an important parameter for us. So let's revise what we have studied in this lecture till now. So first we started with what do we mean by biasing, giving a DC supply. Why do we need the biasing? If we only apply the small signal voltage, what will happen? The transistor will not even turn on. So to turn on the transistor, we will apply a DC bias. Now after DC biasing, we will superimpose the small signal input voltage. If we are after superimposing the small signal input voltage, it will not affect the region of operation. Why so? Because the limit is very small, 2 plus 20, 2 minus 20, very small range it is. So it will not affect the region of operation. Now then we saw that in graph we saw that if we are giving the DC bias to be 2 volt, then the amplification we are getting is this much. If we are giving the DC supply to be 4 volt, then this much amplification we are giving. So at the higher VGS, we are getting more amplification. That means when the slope is higher, we will get more amplification. Now at 6 volt, there will be higher slope, so we will get more amplification. So what do you think here? Now what do you think? That we should keep VGS value to be very high. What do you think? Here, by seeing this graph until now, what you will think that we should keep VGS value as high as we can, because at higher VGS we will have more slope, and if there is more slope, that means there will be more gain, and this is what we want. So we should keep VGS value to be very high, but this is not the case. We have to find an optimum value of VGS, not very high. What will happen if VGS value is very high? First thing, more power consumption. Power consumption will be more. If VGS is very high, that means you have to give more supply from your side. Let's assume VGS is 10 volts, so you have to give at least 10 volt from your side. So this much voltage you will give, that will eat up more power, and who knows, your chip cannot take this much of power. When you are designing chip, on chip there are transistor only, there will be these kind of MOS only, and you have to give them bias. You have to bias all those transistors. So if you bias all those transistors at too much of high voltage, let's assume at 10 voltage, then your chip may burn out. So you cannot give very high voltage. This is the first thing. The second thing is that we will study later on. When we study the amplifier, then we will study that while operating the MOSFET in an amplifier region, while operating the MOSFET as an amplifier, we have to bias the MOSFET in saturation region. What did I say? When you are operating the MOSFET as an amplifier, you have to bias the MOSFET in saturation region, not in linear region. First thing is that you are operating it as an amplifier, so it has to be turned on. It cannot be in cutoff, it has to be turned on. If it is turned on, then there are two possible regions, linear and saturation. So you do not bias it in linear, you bias it in saturation. Why so? The region we will see later on. Why do we bias in saturation region? The region we will see later on. Now the thing is, if I keep on increasing my VGS value, what will happen? If I am increasing my VGS value, what will happen? V overdrive will increase. If V overdrive increases, that means VDS will be lesser than V overdrive, that it will go out of saturation. If I keep on increasing my VGS, my V overdrive will increase. If my V overdrive will increase, that means my transistor will fall out of saturation, because V overdrive is increasing and VDS is small only. So if VDS is small and V overdrive is keep on increasing, so my transistor will fall out of saturation region and I cannot operate it as an amplifier. So when you are operating the MOSFET as an amplifier, you have to make sure that the VGS value cannot be too large. First thing is the power consumption. If it is very large, there will be more power consumption. And second thing is your transistor may fall out of saturation. The reason I explained, and now I will just write down the reason. Okay, I will just write down why I cannot keep VGS value to be very high. We will try VGS value to be high. We will try to keep VGS value to be high, but cannot keep very high. So this parameter becomes very important. Del ID upon del VGS. We will try to get as much del ID by del VGS as much we can. We need del ID by del VGS to be very high, right? So this I will write down. At higher VGS, you get higher value of ये सही से नहीं लगा हुआ क्या, लैग तो अभी भी कर रहा है ना, get higher value of del ID by del VGS and that eventually gives more gain, but while using MOS as an amplifier, you cannot keep VGS value, VGS DC I am writing, VGS DC value to be very high. Like you cannot keep from 2, 4, 6, you cannot keep 6, 7, 8. That much value you cannot keep. There are two regions, right? What are the two regions? Value to be very high. What are the regions? First is the why? First is the more power consumption. Then, and what is the second region? Transistor MOS will fall out of saturation. And why do we need to keep it in saturation? That we will study in the further part of the lecture. In the next video or next to next video, we will see why do we need to bias it in saturation region. So this you have understood, right? Now this del ID upon del VGS is an important parameter, and we have given this parameter a name that is known as transconductance. So what is transconductance? That we show by GM. GM is the transconductance. So what is transconductance? The change in output current with respect to the change in input voltage. This is known as transconductance. I don't need to write the definition. I guess this is more than enough. The change in output current with respect to the change in input voltage. And writing एक बार चेक कर लेते हैं कैसी आ रही है. थोड़ी तो खराब आ रही है आज यार राइटिंग. ठीक है, थोड़ा लैग कर रहा है. I hope you people are fine with that. So the change in output current with respect to the change in input voltage, that is known as transconductance. And more GM, that means more current. More GM means more output current, and more output current, that means more gain. So let's consider an NMOS. This is an NMOS. So what will be the GM for this NMOS? What will be the GM? GM will be del ID upon del VGS. Make sure I am writing capital ID and capital VGS. What do you mean by that? Large signal. That means if I am saying large signal, that means I am talking about DC. Small signal means small signal AC signal. And if I am saying large signal, that means I am talking about DC only. So GM is a DC parameter. GM is a DC parameter that can be found with the expression of del ID by del VGS. Output current divided by the input voltage. That's it. So for triode region for triode means linear region only. So for linear region and saturation region, we can find the value of Gm. So for triode region, what is the value of ID? That is mu n Cox W by L VGS minus VT into VDS minus VDS square by 2. What will be the expression of Gm? Gm expression is only one. Always there is only one expression of Gm, that is output current by change in output current with respect to the change in input voltage. So del ID by del VGS. This is the Gm. So Gm would be del ID by del VGS. So you have to differentiate it with respect to VGS. Mu n Cox W by L. Now you will go inside. VDS is a constant one. VDS is a constant value only. Why it is constant? Because we are differentiating with respect to VGS. So only VDS will come. If you differentiate it with VGS, this will be 1 and VT will be 0. So 1 minus 0 into VDS, that would be VDS only. And when you differentiate it with VDS square, it will be 0 only. So simply your Gm for triode region, came out to be mu n Cox W by L into VDS. Many times students ignore this formula because this is not oftenly used, but they can ask you 1 or 2 marks of numerical kind of question from here. That they will ask you the Gm of triode region. Gm of saturation region is oftenly used. We will find it again and again, but this we don't use again and again. Only once or twice we will see it. So I will take a numerical example so that you remember it actually. Okay. So you have to remember it. Sometimes they can ask you question from triode region as well. They will just simply give the mu n Cox W by L value. They will give the VGS VT value. They will give the VDS value. Then they will say find the transconductance of this given configuration. Then blindly you will go for saturation region. No. First you need to check the region of operation. If you go to know that the region of operation is triode, then you have to apply this formula. The formula will change. The formula for transconductance in saturation region will be different. What that will be? Let's check that. This is transconductance for triode region. Transconductance for linear region I did not write. Okay. So in the next page I am going to write transconductance for saturation region. Transconductance for saturation region. What that will be? Simply write the expression. What is the expression of saturation region current? Mu n Cox W by L VGS minus VT whole square by 2, right? Now if you, what is the expression of Gm? That is del ID upon del VGS. That's it. Output current divided by input voltage. So what will be the expression of Gm here? Del ID by del VGS, that would be mu n Cox W by L, because this 2 will come ahead. So 2 and 2 will get cancelled, VGS minus VT. I hope you know how to take the differentiation, right? So this will be the expression of Gm for saturation region, which is very important. We will use it again and again, but this also you need to remember. This also you will remember. Well and good. You will certainly remember, right? Because this is also very important one. Yeah. So this we have found. Now Gm versus VGS curve, that this we are drawing for saturation region. For saturation region. Just a second, is lagging too much. Just a second. Yeah. So Gm versus VGS graph we were drawing. So for saturation region we are drawing, for saturation region. So what is the expression in saturation region? Mu n C x some constant value Vgs minus Vt. So after Vt it will start. Before Vt the Gm will be 0. Why so? Because current will be 0. When Vgs value is lower than Vt, the current will be 0. So there is no meaning of Gm. It will be 0. After that linear expression is there. But in reality this is not the graph. In reality the graph is different, and that we will study very in depth, but in EDC. That is important for EC guys only. This is not important even for placements. They will not ask you GM versus VGS graph. When we study EDC, I will tell you very in depth for linear region as well, for saturation region as well, how the graph goes something like this. Something like this. So we will study in depth how it goes like this, why it goes like this. So for linear region as well, for saturation region as well, we will study the in-depth concept of transconductance. Even the current expression will change. Something different will be happening, but this is not that much important for circuit analysis part. For circuit analysis part, this is just a graph I made in front of you, so that if anyone asks you what is GM versus VGS, then you can roughly make something. You can tell him those expression, because these expression will be used. But for circuit analysis part, this graph is not important. I just drew it here. When we study device physics, we will study very in depth about it. And electrical guys need not to worry that what will happen if someone asks us this. They are not going to ask you these questions, because that is in depth analysis of device physics. So yeah, just here I drew it. No need to worry about it. Just remember these two things. GM for triode. What is GM? The change in output current with respect to the change in input voltage. What is the expression for triode region? You don't need to mug it up. You can derive it even in your brain. Okay, the current equation I know. You just need to differentiate it with respect to VGS. I never mug up this formula. I just derive it there only, because one step it will take. That's it. Del ID by del VGS, so mu n Cx W by L into VDS. And what about this? That is mu n Cx W by 2L W by L VGS minus VT. Now this is one formula. I told you saturation region is important. So for saturation region, we will write two more formulas. That we will derive from this formula only. This formula we have got del ID by del VGS, that is mu n Cx W by L VGS minus VT. But we will derive two more formulas, because that is important part. You can at any time you need to use any formula. So we will derive two more formulas. So how we will derive that? So what you can see from equation 1, let's just call this as equation 2. From equation 1, what if I do something like this? From equation 1, what do? I will take this 2 here, and one of VGS minus VT downward. There are two VGS minus VT, no? VGS minus VT into VGS minus VT. So I will bring one more VGS minus VT downward. So 2ID divided by VGS minus VT. If I do this, what I will have in the right hand side? What that will have? Mu n Cux W by L VGS minus VT. Isn't it GM only? This expression, this particular expression, isn't it GM only? Yeah. Why did I do that? So that I could make the expression of GM from here. Isn't it equal to GM only? So one more formula I got for GM. What is that? 2ID by VGS minus VT. I will recommend you to remember this formula. I will recommend remembering this formula, because a lot of times we use it. 2ID upon VGS minus VT. Okay. So this is the second formula. This is also very important. One more formula we can get. Again, let's write down the expression of ID. ID expression is mu n Cux W by 2L VGS minus VT whole square. I will multiply mu n Cux W by L on the both of the side. Mu n Cux W by L on both of the side I am applying. Into ID, here also I will apply. Mu n Cux W by L. It will be the whole square, right? Mu n Cux W by L, it will be the whole square. into 1 by 2, this 2 is here, VGS minus VT whole square. I can bring this 2 here, right? So I will remove it off from here. This 2 I have removed it from here and I have brought it here. And this I will take near. So what do you get? This square, this complete expression is a square, so I can take under root on the other side. So from here what do I get? Under root 2 into mu n Cux W by L into ID, that is equals to mu n Cux W by L VGS minus VT. And what is this expression is equals to? Mu n Cux W by L VGS minus VT. Mu n Cux W by L VGS minus VT is equals to GM. So one more formula of GM I am getting. Again I am recommending to remember it. 2 into mu n Cux W by L ID. That's it. Can you remember this? I hope you can remember these 3 formulas, which are very important. Why we are writing these 3 formulas? Because we are going to use MOSFET in saturation region for amplification, and GM is a very important parameter. So we are checking all the possible conditions. One of the expression is this, one more expression is this, and the most common expression is this. At any time you may need to use any formula, so you should be ready for that, right? What if in the question they have given only mu n Cux W by L and ID value? You have mu n Cux W by L value and ID value. From there you can find the GM expression. What if in the question you have ID and VGS value only, or VT value? From there also you can find the value of GM. What if in the question you have mu n Cux W by L value and VGS VT value? From there you can find the value of GM as well. So there are multiple ways of finding GM values. For saturation region only. For triode region, this is the formula. Only one formula is there for triode region. Well and good. Understanding this concept? Let's move on to the next one. So why did we find this GM? Because higher GM means higher gain. Higher GM means del ID by del VGS is higher. That means slope is higher. Slope is higher. That means higher gain. But we cannot keep on increasing the slope because we may fall out of saturation, or there will be more power consumption. Right? So this much we have seen. After that we should start studying the biasing. Now we will see how to bias the circuit, how much bias we can apply, how to bias the circuit, like where I should give the 5-volt voltage source, where I should give the current source, that we will study. But before that I will give one more important concept and some questions we will solve. So these are the questions given in front of you. There are 2 questions. You have to find the transconductance. So M1 and M2 are identical. M1 and M2 are identical MOS with transconductance GM. Both are having GM transconductance. M1, M2, I did not even show. This is M1, this is M2. Both are having GM transconductance. So what do you mean by that? And what do you mean by this line, this dotted line? That means this Vin and Vin are shorted. Both of the transistors are having same input voltage. That's it. This dotted line means at gate you are having Vin, and here also at gate you are having Vin only. This is what this dotted line means. They could have shown it this way as well. They could have shown it like this. But in many questions you will find these dotted line as well. If they had shown like this, then you could have simply understood, okay, Vin is going in this transistor as well, Vin is there at M1 as well, Vin will be going to the M2 as well. But they can show it by dot as well. If they are showing by dot, what does that mean? That both of the transistor is having Vin voltage at the gate. You need to find transconductance of the overall configuration. So this is your overall configuration. That's it. So for your overall configuration, let's make it smaller. This is your overall configuration. So for your overall configuration, what is the input? Vin. What is the output current? I out. That's it. So what will be the overall GM? Overall GM. Overall transconductance. That we can say capital GM I am writing. That would be del I out upon del Vin. So this is what you need to find. That's it. This is your target. You need to find del I out by del V. Now GM of this transistor is given, GM of this transistor is also given. So अरे space ही नहीं छोड़ा मैंने. For transistor M1, for M1, what will be the GM? GM will be this current which is not given. Let's assume I call this I1 and this current I call I2. The current in M1 is I1, the current in M2 is I2. So what will be GM? That would be del I1 by del V, right? And for M2, what will be GM? Del I2 by input is the same only, del V. Now what is your capital GM? Capital GM is del I out by del V. But one thing you can see is that, what you can see? That your I out is equals to I1 plus I2. Say yes or no. I out is equals to I1 plus I2. I out is equals to I1 plus I2. This is the output current, which is the addition of these two current. And based on that, I could find the value of GM. GM is del I1 by del V in, del I2 by del V in. So I can simply replace this del I out with I1 plus I2. What do you get from here? Del I1 by del V in plus del I2 by del V in. What is del I1 by del V in? That is GM. And what is del I2 by del V in? That is also GM. So overall GM will be twice. That's it. Here the overall GM is twice. When we connected them in parallel, the overall GM became twice. What did I do? First I found out the value of GM. That I found out. Then here also again I found out the value of GM for M2 then M1. My first target would have been to find the final expression. What do I need to find? What do I need to find? Del I out by del V in. This is what I need to find. Then I could see that in M1 transistor my GM is del I1 by del V in, and in my M2 transistor my GM is del I2 by del V in, and I out is the combined expression of I1 and I2. So I out is I1 plus I2. So basically del I1 plus I2. So del I1 by del V in plus del I2 by del V in. So GM plus GM 2GM. That's it. That's my answer. So many people confuse it with very complex analysis, like they introduce in MOSFET amplifiers and all those things. But this is not related to MOSFET amplifier. We haven't even studied MOSFET amplifiers. Still, we are able to solve these kind of problems. So it's not related to MOSFET amplifier. There is only one simple expression for transconductance. That is output current by input voltage. Change in output current by change in input voltage. Tell me the answer of this question, this particular question. What will be your overall GM? For this whole expression, this is the DC bias, right? So overall GM is del I out by del V in. Overall GM, overall transconductance. Change in output current divided by change in input voltage, that is this. This is your capital GM. Tell me what is the expression of GM1? The transconductance of M1 and M2 is GM1 and GM2 respectively. So what is GM1? What is GM1? What is that output current for transistor M1? What is the output current for transistor M1? That is del I out. What is the input voltage for transistor M1? That is del V. Isn't it the same as capital GM? That's your answer. That's it. What do you need to find? The overall transconductance. No matter how many transistors you add up, you can add up M3, M4, M5, M6, M7, but the input is applied to M1 only. And the same current will be flowing in all the transistors because they are in series. Let's assume I add up, I keep on adding up transistor. These all are transistor. I keep on adding up M3, M4, M2, M4, M5. But the final input is applied to this transistor only, and the same current is flowing. So overall transistor would be output current divided by input voltage, and the same transconductance will be there for M1 as well. Why so? Because it has the same output current and it has the same input. So your GM is small gm1 only. That's it. So this is your answer. Did you understand it? No need to confuse yourself when you see these kind of question. Just write down the simple expression that I have told. What I have told will be more than enough for you in the examination, in any interview. Just you need to believe in yourself. You just need to write the expression. What is the expression of transconductance? Change in output current with respect to the change in input voltage, del I out by del V in. And what is the transconductance for M1? M1 has the same transconductance, that is output current is I out only, input voltage is V in only. So it would be GM1 only. That's it. So these two questions we have solved. Now we will see one more important parameter. This is not the concept, it is a parameter, that is output resistance. What is an output resistance? If I am asking you find output resistance, if I am asking you find output resistance, what do? I give you a network and I am asking you find output resistance. So here what you will do, you will apply a voltage and get the current out of it. That's it, right? In case of MOSFET, what is our output? Input is VGS, output is VDS. So from VDS, how much current is coming? That will give the resistance. That we call output resistance. So from VDS, how much ID is coming? So del VDS by del ID will give us resistance. And this is the characteristics that we have studied. For linear, it will rise like this, and this one is for saturation. Right? Saturation. Linear and saturation. And saturation we studied about two things. One is the ideal, when your channel length parameter lambda is 0, and one is practical, when your lambda is infinity. We also found out the value of RDS when we studied MOS physics. When we studied the MOS physics, do you remember we found out the value of RDS? When we were studying channel length modulation, we found out the value of RDS in saturation region. What was the expression, if you remember? That was 1 upon lambda ID for practical case, and for ideal case R0 was infinity. Do you remember it? For practical case, the expression was 1 upon lambda ID. If you don't remember, I will make you recall. So this was the ID saturation expression, right? This is the expression of ID saturation. So here, if I do 1 upon del ID by del VDS, what will happen? This is a constant expression, and 1 plus lambda VDS. So you are just differentiating it with respect to VDS. So what will remember? Only lambda will remember. Are you able to understand? So lambda will be there. So what will be your expression? Your expression of RDS would be 1 upon lambda ID saturation, but for ideal case, right? So this we have already derived when we were studying MOS physics. You can check out there. Very simple derivation is there. So this is the practical one. Practical one. What is the RDS for practical? That is 1 upon lambda ID sat ideal. So lambda will be value will be given to you in the question. Then you can find out the value of RDS. How will you find out? Because you have the value of lambda, you can find the ID saturation. But in ideal case, what is the expression of this? That is mu n CUX W by L. This will not be there. This is eradicated. I am asking you to write the ID saturation in the ideal case. In ideal case, lambda will be 0. If you just differentiate it, what will happen? If you just differentiate it, del ID by del VDS, what you will get? Mu n CUX W by L VGS minus VT square into lambda. That's it. Now what is this? ID saturation in ideal case. So that will be lambda into ID saturation in ideal case. So just the inverse we have to take, because RDS is del VDS by del ID. So inverse we have to take. So after taking the inverse, this is what we are getting. And in case of ideal case, what do you get? You get it to be infinity, right? In case of ideal case, you get RDS to be infinity. Why it is infinity? Because if you differentiate this expression with respect to VDS, what will be the answer? 0. Del ID by del VDS will be 0, because there is no expression of VDS for the ideal case. This is for ideal case. Ideal case. In the ideal case, there is no VDS involved. If there is no VDS involved, that means the expression will be 0 only, and if it is 0, the RDS will be infinity. So this is the story for saturation region. Practically it is 1 upon lambda ID, and ideally it is infinity. So MOS in saturation region. So MOS in saturation region, if you are seeing from this terminal, so MOS in saturation region can be replaced with a simple current source. Simple current source, but with the output resistance of RDS. With the output resistance of RDS that has a value of 1 upon lambda ID sat, but ideal case. Current source, constant current source. This is for practical scenario. And what is the scene for ideal scenario? It will simply be replaced with the current source only. This when we are seeing from drain to source terminal. If you are seeing from drain to source terminal, then only you can replace it with the current source. It's not that if I am seeing from here, I will replace it with the current source. No. From here it is not a current source. From output it is a current source. From output it acts like the current source, not from the input side. Well and good. So from output it is acting like a, from output it acts like a current source. So this is drain to source. Here this is also drain to source, and this is current source. Now people say that it is a constant current source. Yeah, this will be a constant current source, but only when VGS is constant. In some question your VGS will be varying. Let's assume my MOSFET is in saturation region. I am telling one of the statement, that is my MOSFET is in saturation region, that I am saying, but my VGS is varying. My VGS is varying, still the MOSFET is in saturation region. So what will happen to my current source? The current source value will also vary, right? The ID versus VGS plot we make. This is our ID versus VGS plot, right? ID versus VDS, sorry. ID versus VDS. So in this region we are working. So here we are saying that it is acting as a current source, but for a particular VGS only. What if my VGS is varying? What if my VGS is VGS2? So the value of current will be changed. Here the value of current is this. Here the value of current is this. So you can't say this will be a constant current source. This will be a current source depending on the value of VGS. That's it. In the saturation region, you can replace the MOSFET with the current source and the output resistance, but the current source will have a varying value with respect to VGS. If the VGS is constant, then the current source will be constant. Did you get this statement or not? So you can't directly say this statement is wrong, that in saturation region MOSFET is replaced with the constant current source. No, MOSFET is replaced with the constant current source only when VGS is constant. If the VGS is varying, even the current source will be varying. So in the saturation region, you can only replace the MOSFET with the current source. Now the value of current source depends on VGS. So I will be a function of VGS. This is what I will write. This I will be a function of VGS. This I will be a function of VGS. Okay, so saying that in MOSFET region, in saturation region, MOSFET is replaced with a constant current source, that is wrong. MOSFET is replaced with a current source. The value of that current source depends on the VGS value. That's it. Well and good. Now let's do the same thing for triode region. But triode region is very interesting. Why it is interesting? Let's check that out. So in triode region, actually there are two regions. One is the deep triode, other one is the sublinear. Let's check that out in the next page. This is nothing written, it is just the expression of triode region current is there. So let's study that triode region more deeply. This is your ID versus VDS plot. So when you draw the curve, there is always a curvature there. It's not that it rises like this and then this. There is a curvature. And what I was saying that in linear region, the current increases linearly. Here I can see that the current increases linearly. But is it happening by this expression? I am saying ID versus VDS is a linear expression. But is that so? See the current expression. In the current expression, there is a term of VDS square by 2. There is a term of VDS square by 2. So is that linear? No, this is not linear because there is a term of VDS square by 2. But when the value of VDS is low, when the value of VDS is low, that means in this particular region, when the value of VDS is low, we can assume this expression going towards 0. Are you getting this point? When the value of VDS is low, we can assume VDS square by 2 going towards 0, and that happens in deep triode region. So we call this region as deep triode region. Deep triode region, and this region is known as this one sublinear. This is not completely linear, this is sublinear. Here VDS square will be coming in action. Are you getting this point? Here VDS. So in deep triode region, what do you see? Del ID by del VDS is a straight line. For a resistance, if I plot V versus I curve, how will the curve look like? Voltage versus current. How will the curve look like? A straight line only. If voltage is increasing, that means current will also increase. So for a resistor, what happens? VI curve is linear. VI curve is linear. In MOSFET characteristic, what do we see? In deep triode region, there is a linear relation between output current and output voltage. So the expression is linear only. So in deep triode region, you can replace the MOSFET with the resistor from output terminal. And what will be the value of that resistor? That we can find by simple expression. So what will be your RDS? And we call it R on actually. We call it R on. The expression that we write, that we call R on, not RDS. RDS expression is given for saturation region only. So for linear region, we generally call it R on. So R on will be del VDS by del ID. That would be 1 by del VDS by 1 by del ID by del VDS. Del VDS. I will put on the charger. Yeah. So R on is 1 by del ID upon del VDS. And for deep triode region, for deep triode region, what is the scene? VDS is very small. By the way, what do you mean by very small? So typically VDS should be lesser than 2 VGS minus VT. That is the typical value. ओके ये तो कुछ गड़बड़ लिख दिया मैंने लगता है. 2 VGS मैंने VGS माइनस VT मान लो 1 वोल्ट है तो VG ना this should not be the scene. It should be VGS minus VT by 2, right? VDS should be lesser than VGS minus VT by 2. because if VGS minus VT is 2 volt, yeah. So typically this is the scene. Typically, this is not a hard and fast rule. It is not any hard and fast rule. Okay, don't remember it. Okay, if it is lesser than that, you just need to compare. If you find that VDS value is typically small, this expression can go to 0, then you can take this as 0. Let's assume if VDS value is 0.1 only. If it is 0.1, what will be the square of that? 0.01. 0.01 by 2. That will be very low. That will be very low. So this can go to 0. So typically your VDS can go to 0. If VDS value is very small, so your VDS can typically go to nearly go to 0. So what will be the expression of ID? Expression of ID will be mu n Ux W by L VGS minus VT into VDS to VDS. So what will be del ID by del VDS? That will be mu n Cux W by L VGS minus VT. And what will be your R on? R on is typically 1 upon del ID by del VDS. That would be 1 upon mu n Cux W by L VGS minus VT. VGS minus VT. That's it. Again, you don't need to mug up this formula. You can derive it anytime. So there are many formulas in this particular video. This R on formula is there. Then one more formula we find. For RDS, these formulas are there, right? But you don't need to mug up anything. You just need to know the expression that okay, what is output resistance? Del VDS by del ID. You know the expression of ID. You can find it out in one expression only, or even in the brain you can think about it. Okay, del ID by del VDS. For saturation, I need to find in saturation region. It doesn't even depend on VDS. It will be infinity. If this is not the if this is not ideal case, okay, it is practical case. Then there is channel length modulation. So lambda factor will be coming 1 upon lambda ID set. That's it. For this deep triode region, okay, deep triode region, VDS square will be going towards 0. So only mu n Cux WIL VGS minus VT will be remaining. So 1 upon mu n Cux WIL VGS minus VT will be my expression. For GM also I don't need to mug up the formula. For triode region I can find, okay, for triode region, what is the expression of my GM? Del ID by del VGS. So expression will be mu n Cux WIL into VDS. That's it. For triode, deep triode, for every region. Here there is no meaning of triode or deep triode. For every region, this will be the formula only. Because here the differentiation is made with respect to VGS. So this expression and this expression are itself going towards 0 only. This one is going towards 1 and this one is going towards 0. So there is no meaning of triode or deep triode. The formula of GM will be the same for both of the region. And then when we talk about transconductance for saturation region, this is very important parameter. So for that we have to remember two formulas. This we can derive very quickly, mu n Cux W by L VGS minus VT. Then the other one is 2ID upon VGS minus VT. This I will keep in mind, 2ID upon VGS minus VT. And the other one is root 2 into mu n Cux W by L into ID. That's it. So these formulas I will remember. Root 2 into mu n Cux W by L ID. So these three formulas I will remember, and then I found out how to find the expression of GM just by the simple formula we have to go. Nothing, no concept of MOSFET amplifier used. Simple formula is there. Then we find out the output resistance. Okay, so this was the summary of this lecture. And one more thing I need to show, that is how will I show the MOSFET in saturation region. Like here I showed the MOSFET in saturation region, so here I will show the MOSFET in triode region. So MOS in triode region. So it will be replaced with the resistance. Gate, source, drain. So it will be replaced from drain to source side. It will be replaced with the resistance of R1. That's it. This is drain and this is source. Okay, in triode region. Triode region. Okay, not in triode region, in deep triode region. MOSFET in deep triode region. Deep triode region. In deep triode region, it will be replaced with RO. The form expression is here. 1 upon mu n W by L Vgs minus Vt. I hope you have understood the complete lecture. By using all these things, whatever that we have studied in MOSFET till now, we have seen the MOS physics, then we saw some question, now we have seen the important parameter. Like first we saw why do we need to bias, like understood why do we need to bias, so that the transistor turns on, then we can amplify it. When we saw the biasing, what did we saw there? We see that del ID by del VGS is a very important parameter. Higher the slope, more the gain. So at high value of VGS, you get higher slope. So then I found out the expression of del ID by del VGS for both of the region, for saturation and triode, and then we saw the output resistance. Output resistance is also an important parameter. When we study amplifier, it will be used there. So output resistance is also an important parameter. So we also studied about the output resistance. So that expression also we found out. Well and good, very easy. So let's move on to the next lecture. In the next lecture, we will see very important assignment. These kind of questions are not asked in GATE till now, but they can be, those questions can be asked any day. So in the next lecture, we will solve those assignments. Okay, thank you.